Hello, this is Rohan Ray. Today we're going to be learning about Kepler's laws. We're going to learn not very in depth right now, but the introduction to some of them. And for the third one of the Kepler's laws, because Kepler he has three laws of motion, planetary motion. We're going to do a mathematical derivation to find out why he came to that conclusion. So first, let's start with the laws of ellipse. Now, I'm not going to tell you the proof of how that happened because I don't have enough time in this video. So I'm just going to tell you anyways, and then you can find out the proof if you want to. If you don't understand it, I'll try to make a video about it. So the first law says that the path of the planets about the sun is elliptical in shape, with the center of the sun being located at one of the foci. Now see, that is called the laws of ellipses. So if you have so if this is a planet and this is the sun would be located at one of the foci of the ellipse. So that's what the first law said. I'll try to do a derivation or proof for why is the sun located at the focus, but for now on, let's move on to the second one. Now the second one, an imaginary line drawn from the center of the sun to the center of the planet will sweep equal areas in equal intervals. See, now that is called the law of equal areas. So let me show you a picture online which I found that will give you the laws of equal areas. Now okay, so suppose this is the sun, right? Here it's again bad focus. Alright, so this is the sun and this is the planet. If you're about to make an imaginary line of the planet, and then each time it rotates for after 1 month, this area would be equal to this area, which would be equal to this area, which will be equal to this area. So if the planet, which is Earth in this case, is going from this distance, it'll take 1 month to go from here to here, and another month to go from here to here, and blah blah blah. So you have 12 of these, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. So and if you draw an imaginary line from sun to each one of those points, you'd find out that this area and this area and this area, they're all equal to each other. So that's the second law of Kepler. Now the third law says that the ratio of the square of the periods of any two planets is equal to the ratio of the cube of their average differences from the sun. Now that's called the law of harmonics. So practically what that says is that here, let me think about it. Alright, so practically what that says is that, so if we have any two planets, right? So suppose we have some planet 1, and then we have another planet 2, right? Wait, suppose we have one planet 1, right? And we have planet 2, right? Now, here, let me draw a better diagram. Okay, so suppose there's the sun, right? And then we have planet 1. And then we have another planet 2. By the way, the second sun is supposed to be at the focus, one of those foci. So practically what is saying is that the period, so I'm going to call the period t of 1 divided by the t of 2 squared on both sides, right, is equal to the radius of one of them. So this radius, I'm going to call this so not the radius, but the distance from the center of gravity of the sun to the distance of the center of gravity of the Earth, of one of the planets. I'm going to call that R1, and the other one, I'm going to call it R2. And that is equal to R1 square, and that's equal to R1 cube divided by R2 cube. So this is practically what Kepler's third law of motion is saying. So if you were to so if by more mathematical derivations, you can say that practically hold on. Yeah. All right. So practically the time period for any planets divided by the the radius or the distance from the center of gravity of the sun to any planet cubed. So the period squared over the distance cube, that will be the same for almost every planet. Now you see that won't always be like that won't always be the same for every planet, but it'd be very, very close, because you see every planet, when they rotate around the sun, they have different eccentricities, which does cause deviation to this value. But that is equal to some constant k, right? Now, during this video, we're going to try to solve the constant k. So I did a mathematical derivation of that, mathematical derivation. So let's get to it. So we have the sun, and then we have the planet, which I would like to call this one Earth. Now, see, the sun has a mass of big M, and the radius and the distance from the center of mass of the sun, or center of gravity from the sun, to the center of gravity of the Earth. See, now I'm going to call that distance r. So let's first draw the free body diagram of the Earth. Now, this is what the free body diagram of the Earth looks like. So we have two forces, right? We have the force of gravitation attraction from the sun, and then we have another force called the centripetal force. Because see, when Earth is moving, it likes to go in towards the sun, because it likes to go towards the sun. So practically, and however, so that's what it wants to do. It wants to go towards the sun. However, ignore my howevers. Though the Earth, it wants to move like this. See, it wants to move tangent to its to the orbital shape that it's moving. So like, since Earth is moving like this, it has a tendency of going this way, but because of the centripetal force, the Earth has, it's not necessarily going this way. It's not necessarily going tangent to this elliptical surface because of the centripetal force, and also I guess the force of gravity, which the sun is attracting to Earth. So it's mainly that the centripetal force. Centripetal force is the reason why the Earth is not going tangent of the elliptical shape. So we have the force of attraction. We have the centripetal force. Now, if you're so let's construct a force diagram, first equation for this. Now, this force equation is centripetal force is equal to the force of gravitational force. Now, in case you did not know that, the formula for gravitational force is equal to G, big G, which is like a gravitational constant, times the mass of one planet, times the mass of another object or planet or a star or anything, divided by the distance between the center of gravity of both objects squared. So that's practically what force of gravitational attraction. That's the formula. Now for centripetal force, it's mv squared over r. So it's the planet that's moving at a velocity or at a speed in a circular path. So the formula for that is mv squared over r. I'm going to plan to do a derivation for the centripetal force later, like the formula for it. But for now, let's just say that's mv squared over r. Now we know that mv squared over r is equal to big G over m times the mass of the Earth divided by r squared. By the way, big M is the mass of the sun, and small m is the mass of the Earth. I'm not sure if I just said that already, but I'm just gonna say it again so that you guys don't get confused. So if you were to do this, so we have this thing divided by is equal to this thing, right? Now the mass of in both sides of the equation of Earth cancels out, and the radius of one side cancels out with one of the radius on the other side. So if you were to do this, you would have velocity squared is equal to big G, which is the gravitational constant, times the mass of the sun over the radius, over the distance of the center of mass of the sun to the center of mass of the Earth, or center of gravity, whatever you like to call it. God dang it, bad focus. Oh, sorry, please do not mind my language. Alright, so since we're dealing with period, that's like one of the things that we're trying to prove to find out the k constant, or to find out the constant between the t squared over r cubed. Let's find out the period. So we know that the Earth is going at some velocity v, right? So and it's going around the sun, right? So what's the distance it goes around the sun at one period? So one period means that the distance it goes around the sun one time. So since this is r, and this is almost like a circle, I mean it's actually an ellipse, but an ellipse with a very low eccentricity. It's almost close to 0, and a circle has an eccentricity of 0. So so to find out the distance that it went, it's approximately equal to 2 pi times the distance from the center of mass of the sun to the center of mass of the Earth. So that's what the approximate distance is, right? Now, so that's for one period of time. Now we want, and then so that's like for one period. Now if you want to find the time in one period, practically what you do is that since we know that the Earth is going at a velocity v, or speed of v, because it's also changing direction, which is why it's accelerating. You just practically do 2 pi r, right? Because that's the distance that it went, and you divide it by the velocity or the speed that it is going. So that would be the time it takes to go for one period. So t is equal to 2 pi r divided by v. So that's practically what the time period is, right? So alright. So that's what. So if you're going to do some algebraic manipulation, v is equal to 2 pi r divided by t, and t is the time it takes to go for one period. So let's plug that part back into this equation right there. So we know that v squared is equal to gm, which g is a capital G, the gravitational constant, times the mass of the sun over the radius. So if you were plugging v to be 2 pi over t, so that would just be 2 pi over t squared, whole squared. 2 pi over r, not 2 pi over v. 2 pi over r divided by t squared, whole squared, is equal to gmr. Now 4 pi r squared, pi squared r squared divided by t squared is equal to big G divided by mass of the sun over radius, over the distance from the center of mass of the sun to the center of mass of the Earth. So if you enumerate that, t squared is equal to r cubed, is t squared over r cubed is equal to 4 pi squared over G over times m. Now see this is a constant. All this stuff is a constant, because 4 pi squared, that's a constant. That's like a number. Like it's not obviously not an integer number, but it's some irrational number. And then g, that's the gravitational constant. Now if you're dealing with MKS units, that would just be 6.67 times 10 to the power of negative 11. And m, that's just the mass of sun. See, the mass of sun, it's not changing. Well, actually, technically it is changing because of the amount of fusion is happening. The two H atoms, they're practically fusing together to make two heliums. So this is practically what it's trying to do. So, well, actually no, it's not change. I guess it's not changing. Yeah, it is technically changing in mass, because fusion deals with change of mass. See, we have this thing called the conservation of mass and energy. However, the formula E is equal to mc squared, which really is equal to change of E is equal to change of mc squared. Whenever you're dealing with fusion fission, the mass of the mass of the total reaction, or the total fusion fission, it always changes, but not a significant amount. So we can ignore the mass of the sun changing, because it's not that significant, even though in later times it would be significant. Like, for example, I don't know, 1 billion years from now, or 5 billion years from now, that's when it becomes significant, because the amount of fusion and fission mainly fusion is happening. And fusion, the more fusion happens with more complex elements, like for example, helium is more complex than hydrogen. It's a sign that the sun is about to die, or not die, but you know what I mean. So sorry, I was going off the tangent there, but really the sun is not that much changing, and technically it is changing, but not significantly enough such that we have to consider about that fact. So the mass of the sun is obviously not changing. So that's practically what the constant is. Now, if you want to find out a numeric answer for that, I'm going to deal with MKS units. So that's kilograms, seconds, newtons, whatever you like to call it. Like all those units, I'm going to deal with those ones. So we know that it's 4 pi squared over 6.67 times 10 to the power of negative 11. Oh yeah, and if you're wondering what the units of big G is, it's Newton meter squared over kg squared. Now, so that's practically the units of the big constant G. Now, what's the mass of the sun? So I'm going to check that out online. I'm going to check the mass of the sun online. Now, see, what do you think I need the mass of the sun in? Well, over here, since we have it in Newton meter squared over kilogram squared, and over here, which one is the unit of mass? Obviously, the kilogram is. So I'm going to search up online the mass of the sun in kilograms. Alright, so the mass of the sun is 1.98 91 times 10 to the power of 30 kgs. Now, let's do some dimensional analysis to find out what the units of the constant is. So 6.67 times 10 to the power of negative 11 times Newton meter squared over kg squared. That's the units of the gravitational constant times 1.9891 times 10 to the power of 30. That's kg. Now the kgs and kg squared, they get cancelled out. And the so practically it's 4 pi squared times kg, that's the units, over 6.67 times 10 to the power of negative 11 Newton meter squared times 1.9891 times 10 to the power of 30. Alright, and I'm going to calculate that right now. It's my calculator right there. I guess I don't need to show you what I'm doing in my calculator, but I really don't care like what you see in my calculator, because my calculator, even though it's a TI Inspire CX, not that I don't want to brag or anything, but it's I don't do important calculations there. I do this thing called MATLAB, and it's a lot better. Just saying. And then divide that by 1.9891, and then divide that by 10 to the power of 30. Okay, so the K constant that I found was 2. Oh, so not the K constant. Sorry, why do I always talk about Hooke's law? Okay, never mind. Okay, so the constant that we found was 2 times 2.97. 562 times 10 to the power of negative 19, and that's kgs over Newton meter squared. See, now kg over Newton meter squared, that's the units of the constant of t squared over r cubed. Now, see, that's the total constant, right? Now, you see that. So, see, every planet would have that constant if only the eccentricity of the path that's going around the sun is equal to 0. That is the only way it'll have that constant. Because you see, we're assuming that the distance that the planet goes around the sun is equal to 2 pi r. Now see, 2 pi r, that's the circumference of the circle, not the circumference of an ellipse. Now, if you want to find out the circumference of an ellipse, you have to do a lot of calculus-based math. Now, if I have time, in which I probably won't have time, I guess I can do it with some calculus involved in it. You know, like just considering the fact of the eccentricity of the orbit around the sun. But for right now, let's not do it. So so this is the exact constant. Now let's check online for some t squared over r cubed, what the value is for as many planets. All right, so for Earth, Okay, so for Earth, it has a t squared over r cubed value of 2.977 times 10 to the power of negative 19, and ours was 2.97562 times 10 to the power of negative 19. So obviously it doesn't have a centricity of 0. Now for Mars, that is equal to 2.975 times 10 to the power of negative 19. That is the closest one is the centricity of 0. And yeah, there are more stuff into it. What else? Okay, and these values, practically, the only reason why they're like 0, 1, 1, 0 is because they only did year squared over the astronomical unit squared. So astronomical unit is practically a distance when you're dealing with stars and galaxies, and that is equal to the distance from the sun to the Earth. That's what an astronomical unit is, and everybody knows what a year is. So, and then our units that we did was seconds squared over meters cubed. So that's why our values were pretty small. But yeah, so these are the values in year squared over astronomical unit cubed, and those are the values for that. So thank you for watching this video. I'm really if you watched if you watched this video, like if it took 20 minutes to watch this video, to take 20 minutes of time to watch this video, I'd really appreciate that. Or at least like this video, because I'm trying to fish for likes, and obviously I don't have that many likes. And Rahul Ramesh, make sure you like this video. Alright, bye.